Hey guys, how's it going? Welcome back to Tensor Calculus. Last time we started off, or we actually got to the definition of rank 1 tensors, and then I gave an example of a contravariant tensor, rank 1, and an example of a covariant tensor, rank 1. And those were the tangent vector and the gradient vector field, gradient vector field, tangent vector field. So today we're going to start off with higher order tensors. So, well, actually, let's just finish up with something before we get to higher order tensors. Last time we talked about ti up, ti prime up was partial xi prime up, partial xk, tk up. And that was a 1, 0 tensor. 1, 0 tensor. Vi prime down was partial xk, partial xi prime down, vk, or sorry, yeah, vk down. That was a 0, 1 tensor. And we gave an example of both of those. We had a contravariant tensor to start off with, and then we had a covariant tensor, which was the gradient. So let's look at something called invariance. So definition. Let's see. An object or quantity that is independent of coordinate system is called invariant. For example, what are some invariants? Well, a vector itself is actually invariant. It has a length and a direction, or a magnitude and a direction. So, example, a vector v is invariant. The vector itself is invariant. Its components may not be. So the vector v has components possibly in a certain coordinate system. Maybe with respect to the covariant basis, you could say vi up, zi down, where vi are not invariant, right? Your components of your vector do depend on the coordinate system, but the vector itself doesn't depend on the coordinate system. The vector itself has a fixed length and a fixed direction. So the vector itself is invariant, but its components would depend on the coordinate system you're talking about. Also, it would depend on the basis that you're referring to. Are you doing the covariant basis or the contravariant basis of the coordinate system? So another thing could be something like the gradient itself. That's a vector field. So the rate of change, or the gradient, would be another example. Also, scalars. Scalars are invariant, like the gravitational constant. If you were to say gravity, g equals 9.8 meters per second squared, regardless of coordinate system. So things that are scalars, those are invariant. They have no indices, basically. So layman's way to say this, so in layman's terms, layman's, right, L-A-Y, in a layman's terms, anything without indices, anything without indices is an invariant. So it's just something that does not depend on the coordinate system. So, theorem says let SI up and TI down be components of appropriate tensors i.e. vector fields that are either contravariant for S and covariant for T. Then the product E, which is SI up, TI down, is an invariant. So that's our theorem. Basically, if you take a product of a covector and a contravariant vector, or just vector and covector, you get something that is invariant, something that's constant. In any coordinate system, it has the same value. So, any coordinate system, this thing has the same value. That's what it means to be invariant. Kind of like length. If you calculate arc length, it shouldn't matter if you calculate that in Cartesian or spherical or cylindrical or whatever coordinate system, the length itself shouldn't vary. So that's the idea. That's what it means to be an invariant. So let's look at an example here. So example, this example says, suppose F, capital F, is the temperature I think that's a U, temperature, I think it's an E. Temperature, so let capital F be the temperature at a point in space at time t. Let x1, x2, x3 denote the coordinates of a position in space at time t. Then the tangent vector. Which is, we'll call it t superscript I, which is dxi dt, is like velocity. Right? The tangent vector derivative of the position over time would be velocity. So the tangent vector components. And the gradient vector components, we could call them G, or down we'll call it, would be partial F, partial XR. Then the directional derivative then the directional derivative, or really just the rate of change of F being the temperature, by the chain rule is, so how does the temperature change over time? dF dt would be equal to partial F partial xi dxi dt, which would really just be gi down ti up, which by our theorem is an invariant, which by our theorem, I shouldn't say directional derivative, I should say the time rate of change of the temperature. Sorry, then the time rate of change of the temperature by the chain rule is this. So, which by our theorem is an invariant. That makes sense, right? The temperature changing only depends on time, right? You don't care what coordinate system you're using. It doesn't, that's irrelevant. The temperature changing over time is independent of coordinate system. So that is an example of an invariant, and how we could show that it's an invariant. We just show that it's a product of a vector and a covector. So that's our little bit of a discussion, just to kind of build off what we talked about last time. So now let's look at higher order tensors. So now higher order tensors. And we're going to start off with second order tensors just to kind of get our feet wet, and then the generalization is very similar. So first of all, second order tensors. All right, so definition. A matrix field what does that mean? That just means a matrix of functions. Kind of like we had a vector field was just a vector of functions. A matrix field. Matrix field is a contravariant tensor of order 2 if its components transform as ti prime up j prime up equals partial xi prime up partial xr partial xj prime up partial xs trs up. And we call this a 2-0 tensor. 2 contravariant, 0 covariant indices, so it's a 2-0 tensor. Notice there's a double summation happening on the right side. So to get the components in the new coordinate system, you do a double sum of these partial derivatives times the components of the old coordinate system. So quite an involved process if you're to actually do it out. But we're not actually doing it out right now. We're just writing down the general definition. So that is the definition of a 2-0 tensor. It's basically a matrix of functions whose elements transform a certain way when you change coordinate system, and they change this way. You take the Jacobian times a different element of the Jacobian times and you add all those together times the original elements in the original coordinate system. So there's like a double sum happening over those Jacobian elements. So 2 sets of Jacobian elements. So that's a 2-0 tensor definition. A matrix field is a covariant tensor of order 2 if its components transform as follows. And I'll do V I prime down, J prime down equals partial x r up, partial x I prime down, partial x s up, partial x j prime down, b r s down. And we call that a 0-2 tensor. 0-2 tensor. Because it has 0 contravariant indices and 2 covariant indices. So it's a 0-2 tensor. Right? Don't forget what we talked about. 2 indices means basically like a matrix. So the number of indices determines the dimension of the matrix. If it's a 0-1 tensor or 1-0 tensor, it's just a vector field. If it's a 2-0 or 0-2 tensor, it's a matrix field. We haven't talked about higher order tensors, or sorry, we haven't talked about higher dimensional tensors. Dimension being the size of the matrix. Not the size, but the dimension of the matrix. So, kind of alluded to it previously, but let's look at the last one, definition. A matrix field is a mixed tensor of rank 2 if its components transform as follows. And here we'll say S I prime up, J prime down be equal to partial x I prime up, partial x r, partial x s up, partial x j prime down, s r up. Oh, let me use a different variable. We'll use a little t here. T down, little t down. Didn't want to have an S capital and a S lowercase. So we use 2 different letters. And we call this a 1-1 tensor. So this is a 1-1 tensor. So it still has 2 indices, but it has 1 up and 1 down. It has 1 contravariant and 1 covariant index. Meaning the elements in the rows, if you were to look row-wise, those rows would transform contravariantly, whereas the columns would transform covariantly. So if you were to take the, it's kind of the way to interpret that a little bit. If you were to sum over the columns of the old coordinate system, actually if you were to sum over the rows of the old coordinate system, it would transform covariantly. All right, let's look at, let's see, a even higher order tensor. So let's see, we got 2, 0, 0, 2. We did mixed tensors. Let's, one thing before we move on to an example. there's a theorem, and it says if Tij down is a covariant rank 2 tensor, then its matrix inverse Tij inverse is a contravariant rank 2 tensor. We call it Tij up. So if you ever see a tensor with 2 indices down and then the same letter, the same tensor with 2 indices up, it's really just the matrix inverse. So contravariant order 2 tensor is the matrix inverse of the corresponding covariant tensor order 2 or rank 2. So cool. Any questions? I'll take a second, slow down a little bit, answer any questions that you guys have. The second part here is even higher rank tensors. So if you have an even higher rank tensor, actually it's just going to follow the same pattern. So, and later on in the book, there's something called the Riemann curvature tensor. So example, the Riemann curvature tensor is something like Ri up, Jk L down, would transform as, and we'll call it Ri prime J prime K prime L prime. It would be partial X I prime, partial X P, partial X Q, partial X J prime, partial X PQ. I don't want to use R. I can use R, it doesn't matter. Lowercase. They look different. Partial X K prime, partial X S, partial X L prime, R P up, Q down, R down, S down. So there's a quadruple sum happening on the right hand side, but we don't have to write out all that because we know the Einstein summation is kicking in. But technically there's a quadruple sum happening on the right hand side. So that's something called the Riemann curvature tensor. It has a very particular definition. We have no idea what that is, but it turns out to have 4 indices, 1 contravariant, and 3 covariant indices. So we call this a 1-3 tensor. So it's a 1-3 tensor. The Riemann curvature tensor. And it turns out you can actually raise and lower indices. So there's another form of the curvature tensor called, I think it's still the Riemann curvature tensor, but has a slightly different name. And it has all 4 indices down, so it'd be covariant 0-4 tensor. And we'll talk about how to raise and lower indices when we get to chapter 5. But for now, that's just all we have for the Riemann curvature tensor. We actually won't even be able to really come back to it at the end of this class. All we're going to get through is the covariant derivative. But Riemann curvature tensor is actually related to covariant derivative. So it's the, I don't want to give it away. Leave something for you to desire when you leave this class. All right, so another example. Another example is the Kronecker delta. The Kronecker delta, delta ij, is a mixed tensor, a mixed rank 2 tensor. So, why? Well, let's look at how it transforms. If we look at delta, so we look at delta, we'll call it ij down, and let's say we multiplied it by partial x I prime up, or yeah, let me use a different letter. We'll call it r prime up, partial xi down, and multiply that again by partial xj up, partial xs prime down. Well, what would that mean? It means I and j have to be the same thing, right? So this delta tells me that I equals j. So if I is equal to j, and that delta turns into a 1, I get partial x r prime, partial xi, partial xi, partial x s prime. Well, now there's a summation happening here. This is really just a multivariable chain rule expanded out. So undo that chain rule, we get partial xr prime, partial xs prime. That's by undoing the chain rule. What's partial xr prime, partial xs prime? Well, that's delta r prime s prime. So that means the Kronecker delta transforms like a mixed tensor rank 2. So Kronecker delta transforms like a mixed rank 2 tensor. So there's an example of a mixed rank 2 tensor, the Kronecker delta with one index up and one index down. So, definition. An affine tensor. An affine tensor is a field whose components transform like tensor under affine change of coordinates. But maybe not any change of coordinates, just affine change of coordinates. Then we call it an affine tensor. And we'll see an example of that in chapter 6. The so-called Christoffel symbols are affine tensors. They're not actually tensors, they're pseudo-tensors. Like they only are tensors under affine change of coordinates. So not a general curvilinear change of coordinates. only in an affine change of coordinates. We'll see an example of this in chapter 6. Let's find the Jacobian of a transformation and the inverse of the Jacobian. So, example. Now we've done this a lot. Just do it one more time. Example. Let's say we got transformation here. Let's say our transformation T is change of coordinates. X1 prime is equal to x1 times x2, and x2 prime is equal to x2 squared. Find A, Jacobian matrix, and B, the Jacobian matrix inverse. So that would be the Jacobian, and the inverse is actually the Jacobian of the inverse transformation. So this is the Jacobian matrix of the inverse transformation. And we know that it will be the matrix inverse of the original Jacobian matrix. So solution. So this is our change of coordinates. Yes, so quiz on Monday. I'm thinking, I'll tell you the plan in just a few minutes, like once we kind of get closer to the end. I'll tell you the plan, give you an update. So let's find part A, the Jacobian. So the Jacobian is going to be partial x1 prime, partial x1, partial x1 prime, partial x2, partial x2 prime, partial x1, partial x2 prime, partial x2. So the Jacobian matrix is going to be x2, x1, 0, 2, x2. Just taking those partial derivatives from our change of coordinates. Differentiate the x1 prime variable with respect to x1, you get x2, etc. So that's the Jacobian matrix of the transformation. What's the inverse transformation? So part B, to find the inverse Jacobian, I need to find the inverse transformation. So what's the inverse transformation? Well, I need to solve x1 in terms of x1 prime, x2 prime. And same thing for x2. Let's see. x2 is going to be square root of x2 prime. And then x1 would be x1 prime over x2. So x1 prime over x2, but that's square root of x2 prime. And we'll assume here x2 prime is greater than 0. Also, we'll assume x2 is greater than 0. So that's the inverse transformation. That's how we would go back to the unprime coordinate systems if we had the prime coordinates. So that's the inverse transformation. And now take the Jacobian of that. So J inverse B partial x1 prime, partial x1 partial x2 prime, partial x2 partial x1 prime, partial x2 prime. Take those derivatives. Let's see, partial x1 prime will just be 1 over square root of x2 prime. Partial x1, partial x2 will be negative 1/2 x1 prime over x2 prime to the 3/2. So differentiating that with respect to x2 prime. Let's see, differentiate x2 with respect to x1 prime, we get 0. And differentiate x2 with respect to x2 prime, we get 1/2 1 over square root of x2 prime. Okay, cool. What if we look at this inverse? What is the inverse of this matrix? Well, the inverse of this matrix would be 1 over the determinant, which would be 2x2 squared, times the adjoint, so it would be 2x2, x1, negative x1, 0, x2, which would be 1 over x2, negative 1/2 x1 over x2 squared, 0, and 1/2 1 over x2. And if you were to substitute these in here, you would get this matrix here. So look at that. The matrix inverse is actually the inverse Jacobian, or the Jacobian of the inverse transformation. So good stuff. Good stuff. So we'll call this thing J prime. Jacobian of the prime coordinate system equals inverse Jacobian. Good stuff. Questions? All right. Example. If vector v is given by vi up, zi down, and we consider the partial derivatives we'll call it Tij, defined to be partial vi up, partial xj, show that Tij transforms as Ti prime up, J prime up equals TRS partial xi prime up, partial xr partial x s, partial x j prime. However, we add something to it. T r up partial squared xi prime partial xr partial x s partial x s partial x j prime, i.e. not a tensor. So i.e. not like a tensor. Meaning partial derivatives of tensor components need not transform like a tensor. So that's a little bit of a problem that we'll readdress in the future. But taking derivatives of tensor components need not produce a tensor operation. Like it's not a tensor itself. This partial derivative is not a tensor. Even though it might have two indices, it would not be a true tensor transformation. So let's look at the solution. So how do we show how it transforms? So solution. Let's look at partial t I prime partial x j prime. And since ti prime is a tensor, it transforms like a tensor. Ti prime, or partial xi prime, partial xr, tr. So it does transform like a tensor. We have partial ti prime, partial xj prime would be partial xj prime of partial xi prime, partial xr, tr. So what I should say at the beginning is really just say consider this derivative. And that is actually ti prime j prime. So consider the ti prime j prime. So that's what this is. Well, since ti, or t, is a tensor, its components are a tensor, transforms this way in red over here. So then differentiating right here means we're really differentiating this thing right here. And now we can use the product rule. So now use product rule. So by the product rule, this would be partial tr, partial xj prime, partial xi prime, partial xr, plus tr, partial xj prime of partial xi prime, partial xr. So now what? Well, if we want to differentiate tr with respect to j prime, we first go through the unprimed coordinate systems to do so. So the multivariable chain rule, we go through the unprimed coordinate system. So we could say partial tr, partial xs partial xs partial xj prime partial xi prime partial xr plus tr. And now I want to differentiate prime with respect to prime. So we actually go through the unprime coordinate system again. This is going to be partial squared xi prime partial x s, or you could use a different letter if you wanted, and then partial x r, and then partial x s partial x j prime. And now this first term is t r up s down partial x s partial x j prime partial x I prime partial x r plus tr partial squared xi prime partial x s partial x r partial x s partial x j prime. So ti prime j prime transforms like this, i.e. does not transform like a tensor. So this is not a tensor transformation. So, like I said, the multivariable chain rule is literally the most important thing from multivariable calculus that you could remember. So, I hope it works. I hope it is clear to you. I hope it's working for you. Multivariable chain rule, literally so important. Now, any questions? Just take a second. Try to slow down a little bit. See if there are any questions. If not, we can do one more example at least. Next time we'll do some more examples. Look at a worksheet. I may post a worksheet over the weekend or today. Yeah, just I have a few more examples to work next time, and we can also go over the worksheet. We may push the exam to Friday so we can do our quiz Wednesday. So heads up, we probably will push the exam to Friday so we can do a quiz Wednesday after we start covering some chapter 4 stuff. I don't know, we'll see. I may just do a separate video and cover the worksheet on there. So, does that sound good? Rachel? Example. Let's use the tensor for what it's created to do, or what we know about it. So this is actually going to change the components for us without us having to go through that explicit process of finding the explicit basis vectors and do all that mess. We're going to calculate the components in a new coordinate system. Probably tomorrow I'll have a good idea. I'll probably post the worksheet tonight or after our lecture here, and then I'll try to get a video up or something tomorrow. And then Monday we can do some more examples and have our quiz Monday. Yeah, I'll let you know over the weekend before Monday. So probably by tomorrow. All right, so now let's use a tensor. The best way, or the only good way there is to use it, and that is to calculate or to find its components. This is so wrong for me to say. The only good way to use it. This is like the worst way, actually. You don't really want to work in any coordinate system. But regardless, let's find the components of the tensor in a new coordinate system if we know the components in an old coordinate system. So calculate, we'll call it vi prime in the xi prime system if the original components v are x2 comma x1 plus 2x2. Of course, I'm assuming covariant components. So these are the covariant components. V R down, we'll call them. So this is like V1 down, and this is V2 down. So that would be multiplied by the corresponding contravariant basis vector. But we're not going through all that mess because we can calculate them regardless. But I need to give you a change of variables. So how do you get from prime to unprime, etc.? So the transformation t is given by change of variables. x1 prime equals x2 squared and x2 prime is equal to x1 times x2. So kind of like the other change of coordinates, but just a little different. So what is the Jacobian? Jacobian is going to be 0 to x2, x2, x1. Okay, solution. What do we know? We know vi prime down is equal to partial xr partial xi prime vr down. So what would that mean? Explicitly, that would mean v1 prime would be equal to partial x1 prime v1 plus partial x2 partial x1 prime v2. So I need the inverse Jacobian elements. So what are the inverse Jacobian elements? J inverse, it's going to be one over the determinant, 1 over, it's going to be negative 2x2 squared times the adjoint x1, negative 2x2, 0, and negative x2, which would be negative 1/2 x1 over x2 squared, 1 over x2, 1 over 2, 1 over x2, 0. So let's calculate those. Let's see, what have we got here? What's this one? This one is supposed to be partial x1 prime. And what's this? This is supposed to be partial x1 prime, or sorry, partial x1, partial x2 prime. And this one is supposed to be partial x2, partial x1 prime, and this one is supposed to be partial x2, partial x2 prime. So this is going to be, let's see, partial x1 prime is negative 1/2 x1 over x2 squared times v1. Well, v1 is x2 plus partial x2, partial x1 prime is 1/2 1 over x2 times v2, which is x1 plus 2x2. So let's see what we get. If we simplify that, we should get negative 1/2 x1 over x2 plus 1/2 x1 over x2 plus 1, which is 1. So our component in the prime coordinate system for v, the covariant component in the prime coordinate system, v1 prime is just 1. Okay, what about v2? v2 prime be equal to partial x1 partial x2 prime v1 plus partial x2 partial x2 prime v2. So v1 and v2 stay the same, but the partials, we changed those. So partial x1, partial x2 prime is supposed to be 1 over x2. 1 over x2 times v1, which is x2, plus 0 times x1 plus 2x2. Again, that is just 1. So the v in the prime coordinate system, its components, represented by 1, 1 in the prime coordinate system. So that would be v equals 1 times z1 prime plus 1 times z2 prime. Whereas could also represent it in the unprime contravariant basis as x2 times z1 up plus x1 plus 2x2 z2 up. So you have two different representations with respect to contravariant basis in two different coordinate systems. So that is way easier than what we did back in chapter 7 when we were explicitly like finding all the basis vectors and like inverting them and trying to do all that mess. Man, that was a pain. Well, now if they're tensor components, we know how to find them in a new coordinate system using these partial derivative transformation properties. So that's the beauty of tensors right there. Kind of sidestep all that basis vector junk. So quite intense. Hopefully you can slow it down, go back and watch it again, make sure it's all clicking. But that's it. That's pretty much it for today. We're going to do some more examples on Monday. Like I said, I'll post a worksheet here probably in a few minutes, and then I'll try to put out a video over the weekend that just kind of goes through that worksheet kind of slowly. But yeah, we'll do some more examples on Monday. Let's see what we got coming up on Monday. I got an example here. Yeah, not too crazy, I guess. I don't know, we'll find out. And another example, let's see what this one is. Tensor component. Oh yeah, this one's good. No, we'll see. We'll see a few more examples on Monday. And then, yeah. Cool. there are no questions, you're free to check out. Have a good weekend. Smash the like button. Just kidding. I mean, you can if you want. But yeah, just talk to you guys later. Have a good weekend.